The activity you just did looked at two what we would call estimators. And the estimators are tools that we use to estimate something in a population. So let's just review what our population is in this example. What is our sample? What is the true thing we're trying to estimate? And what is the statistic that we derive from the data? So each person got a cup of 20 pieces of paper and each one had a measurement on it. So we would regard those 20 measurements as the population that we are interested in. And each time we gather data from this population, we're taking a sample of 10. So that's the sample. And we're trying to estimate the true average heart rate in the group of 20 measurements. And we're doing this by calculating a statistic, which is the sample average, the sample mean heart rate for each of the 10 measurements that you randomly select from the cup. Okay? So in the notes, you'll see a summary of those four things: population, sample, and then the true thing we're trying to estimate is actually called a parameter. We've seen that before. Parameter, and then the statistic. Okay? Then I asked you to find the sample range. So the sample range is going to be the difference between the largest and smallest heart rate in the sample that you took from the cup. And then you made two dot plots on the board, one showing the sample mean that you calculated from the sample of 10, and it should have looked something like this. Okay, we should have had a collection of points estimating the sample mean, and we should have seen some variability. Okay, so then I asked everyone to, or someone, to find the true population mean, the true mean heart rate for the 20 measurements. And that should have been something like 73.4. So that's what we call mu, the true mean, 73.4. And looking at this all together, we should notice that the sample measurements are centered around this value. So most of the time, the sample mean is fairly close to 73.4, and then we see some extremes. Somebody might have gotten a measurement close to 82. We might have gotten something as low as 67 or 66 as our sample mean. Now this just shows the random variability that happens when we take different samples repeatedly from a population. Okay? This is called a sampling distribution. And you'll also see this summarized in our notes that I've shared with you today. So the sampling distribution shows the distribution of a statistic when repeated samples are taken. Okay? The next thing I asked you to look at was the sample range. So in each sample, you took the difference between the largest and the smallest measurement. And it should have looked something like this. So I had asked everyone to do this 5 times and plot your measurements on the board. Then I asked you to find the true range of all 20 measurements. The true range of all 20 measurements is 52. And in our efforts to estimate the true range, you clearly notice that it's impossible to find an estimate that's larger than 52. That's the largest the range could actually be. So all of our estimates are going to be lower than the true range. Now this is an example of something called bias, which we encountered before in chapter 4, and we knew that bias was a systematic difference between our estimate and the truth. We're going to look at bias in a slightly different way now. And we're going to attach the idea of bias to something called an estimator. And the estimator is the tool that we use to estimate something or make our best guess at something true about the population. Okay? So in our first example, our estimator is the sample mean. That's the tool we're using to try to estimate the true mean. And in the second example, our estimator is the sample range. That's the tool we're using to try to estimate the true range. And then all of our observed values, all these orange dots, are called estimates. Okay, similar, but the estimates are what we observe, the realizations based on the sample data that we collect. Okay, so keep in mind the difference between an estimate and an estimator. We can talk about the estimator as this tool, and we either describe the estimator as biased or unbiased. So in the first example, the sample mean would be considered unbiased and that is because there's no systematic error in estimating the true mean. There's just as much variability above the true mean as there is below the true mean, and we see a symmetric distribution. Okay? So we're not off in one direction, where our error is not consistently in the same direction. And on average, if we take the mean of all these sample means, we should do a pretty good job of approximating the true mean. Okay? So we would call the sample mean an unbiased estimator of the truth. Okay? Then we move to the range. And we would call the range a biased estimator because it is consistently lower or equal to the truth. There are rare cases when the sample of 10 contains the true minimum of the population and the true maximum of the population. So in those cases, we're going to get an estimated range of 52. Well, that's the best we can do. All of the other estimates are lower than the range. So the range is a biased estimator. When we encounter what we call a biased estimator, we can't use it to estimate the truth about the population. So the range cannot be estimated using sample data. It cannot be accurately estimated using sample data. But the mean, the sample mean, is a good tool to estimate the true mean of the population. Okay? So that's our discussion of bias, and you'll see that summarized in the notes that I've shared. Now, one more thing to talk about is variability. Our focus in this activity is bias and variability. Okay? So anytime we try to estimate something about a population, we encounter variability. And that variability has to do with the differences that each person sees in the sample data that they collect from the population. Okay? Just by random chance, some groups may have several low measurements for the heart rate and would therefore have a low sample mean. And on the other end, some groups may have several large measurements for the heart rate. So we see a higher estimate. Okay. Now, we've asked this before in chapter 4, and that question involved, what can we do as the statistician? How can we control the variability in our sample data? So the sampling distribution, showing the variability in the sample mean, could be made more consistent by taking larger samples. In our simple case of 20 observations, where the population is only 20, if I chose a sample size of 20, what would happen every single time? We would get an estimate exactly equal to the true mean. Our estimates would be 73.4 beats per minute, and we would have estimated the true mean exactly. Okay? So when the sample size is equal to the size of the population, we see no variability in the statistic that we're calculating. But as the sample size gets smaller, we see more and more variability. So imagine on the other extreme, taking samples of only 2. We would see a lot more variability in our results. Okay? So at this point, you should understand what variability and bias mean. And to illustrate those ideas, take a look at the notes that I've put together that summarize what we're going to be doing in Chapter 7. Okay? Chapter 7 is all about sampling distributions and how we use sample data to estimate something about a population. We want to make a judgment about a larger population. So please read over the notes in the introduction to Chapter 17, and you'll have some chances to practice identifying the population, the sample, the parameter, the truth, and the statistics, so reading in context. Okay, and then at the very end, you're going to see this summary of bias and variability and what it all means. So it's helpful to see the dartboard analogy, where we can see something that has high bias and low variability, where the darts are missing the target consistently, but there's not a lot of error in the placement of the darts. Okay, so that would be high bias and low variability. And we have another case of low bias and high variability. Notice that the estimates, symbolized by darts, are all more or less centered around the true target, but they're not very consistent. Then we have the worst case scenario, which is high bias and high variability. The estimates are consistently different from the truth, and there's a lot of error. Finally, this is our best case scenario. This is where we have very little bias or no bias at all, because the estimates are close to the truth, and we have low variability. In these cases, our estimates are very reliable, and this is what we always want as statisticians. Okay? So throughout this chapter, we'll be talking about techniques we can use to avoid bias. We talked about those in chapter 4 a little bit. And we'll also really focus on quantifying the variability. So what I mean is measuring the variability. And some of our familiar tools will come back to us, like the standard deviation, maybe the IQR. But remember, we're always going to want to use measurements that are inherently unbiased. So we have found that the range is a biased estimator. But we will find that the standard deviation is actually not a biased estimator. It can be used to approximate the variability in a population. Okay? So from here, go ahead and read over the notes, and then give the problems in Chapter 7 a try. This is an assignment 7.1 that's going to help you start thinking about sampling distributions and some of the terms and concepts that we've gone over in the activity and in the notes. Okay? Good luck. Thank you.